In our past few videos, we've discussed a lot about systems of equations. And essentially, these were sets of multiple equations that had multiple variables to be solved simultaneously. So for instance, we might have had something like 5x minus 4y equal to 2, and 6x minus 5y equal to 1. And together, these represent a system. And as a system, in the same way a single equation with a single variable has a single solution that makes the equation true, right? Makes both sides of the equal sign actually equal. This system of equations has a pair of solutions, an x value and a y value, that when plugged into both will make both of the equations true, right? They'll have some xy pair as its solution. In the case of this particular system, that solution is 6, 7, which is to say if we plug in 6 for x and 7 for y into both of these equations, we'll find that both statements are true. And we've talked about a few different methods at which we can solve these. We could use what's called the substitution method, for instance, where we solve for one variable as an expression and then take that expression and plug it into a different equation, and then get a single equation with a single unknown, which we can solve from there to then plug back into our original. We could also use what we called elimination, sometimes otherwise referred to as the addition method, where we could actually add our two equations together so that we could cancel out one of the variables, again leaving us with a single equation with a single unknown, which we were able to solve and then plug back in to get the other variable. And these are both fantastic methods, and when we're working them out by hand on paper, they work really, really well. However, as computers started to come around, as those started to be invented and people started to program them and started to want to delegate some of these types of problems that are more algorithmic in nature to solve to a computer, which can, do it faster and more efficiently and more accurately than human beings often can, the desire to find an algorithm that works really well for computers started to arise. Using a substitution method or using an elimination method, human beings can be really good at that on paper. That's a little trickier for a computer to do. Now, what computers are really good at is dealing with lists of numbers. And so what we'll find here over the next couple of videos is that if we utilize lists of numbers and utilize them in a particular way, we can come up with some algorithms that allow us to solve these sorts of problems just as effectively, but more in the style of how a computer might do it. And now these particular types of numbers, we have a name for them and we're going to call them a matrix.
Do you want to know what it is? The matrix is everywhere.
And basically all a matrix is going to be is some list where we list some numbers, maybe A1, A2, A3, or however many you have across a row. And then maybe you have another row, B1, B2, B3, or for however many numbers you have, and so on and so forth for as many rows as you need. Effectively listing our numbers out in some kind of m by n grid, right? Listing m rows and n columns. Now, these types of mathematical objects, right, a matrix, deserves a whole coursework of study, if not more. There's lots of nuances and lots of things that we can do with these that would be explored fully more so in a class like linear algebra. For our purposes here, we're just going to kind of take a very narrow slice of that, specifically for the purpose of solving systems of equations. And so this video and the following one will maybe not serve so much as like a really in-depth analysis of linear algebra or go far into the details of the theory, but really focus specifically on that algorithm that we can use, or at least an algorithm that we can use to solve systems of equations the way a computer might. And so in our case, we're going to focus specifically on square matrices, in other words, that have the same number of rows and columns. And more specifically, we're going to take those square matrices and evaluate what is called the determinant of them. Essentially, all that is if we had some kind of square matrix, like for example, A, B, C, D, it's taking those four numbers and turning them into just a single value. Now that's a lot of sort of background, big picture, summary info, but I think this will start to make more sense when we actually get into computing some of these. So let's actually try to define here what is in fact a determinant. Now, like I said, these are going to be defined on square matrices, and first we'll start with just a 2x2 grid. And so we'll say that the determinant of the matrix, and here's where we'll label an arbitrary 2x2 matrix. We'll call this A1, B1, representing the first row with A and B. And then we'll call this A2 and B2, so representing the first row with ones, the second row with twos, the first column with A's, the second column with B's. And so we have the matrix A1, B1, A2, B2. And in particular, when we denote this, like when we write down the determinant, so when we write the matrix, we'll use these square brackets, but when we write the determinant of the matrix, we're going to use these vertical bars, kind of like an absolute value sign. And so we denote this A1, B1, A2, B2 with the vertical bars when we're talking about the determinant. Is defined by the determinant of any matrix, so any collection of four numbers like this, would just be the product of this diagonal here, right? So the first element and the last element, A1 times B2, minus the second element and the third element. So the product of this diagonal here, B1 and A2. And that's really it. The determinant is just using this particular algorithm, this particular difference of products, to get a single value from the four that were given in the matrix. And so since this is all still pretty abstract, let's actually dive into an example and see how this works, because I think that will be the easiest way to get a handle of what specifically we mean here.
Unfortunately, no one can be told what the matrix is. You have to see it for yourself.
So let's say we have a matrix 10, 9, 6, 5. Just a 2x2, we've got 2 rows and 2 columns, and we want to take the determinant of that. So again, we're going to write this with the vertical bars here. And so we have 10, 9, 6, 5. And what we mean when we say this, right, again, for some arbitrary matrix, I'll call it A, B, C, D this time, we're just taking the product of this diagonal, so A times D, and subtracting the product of this diagonal, B times C. So for our particular case here, we're looking at this diagonal here, 10 times 5, and then subtracting this diagonal here, the product of these, 9 times 6. And then we would evaluate this. So 5 times 10 gives us 50. 9 times 6 gives us 54, and the difference between 50 and 54 would be minus 4. And this is all it is to get our final answer. Right? We started with this 2x2 grid, so 4 numbers. We apply this particular algorithm and we end up with a single real number. That's what we call the determinant. And that's really all there is to it. The product of that first diagonal minus the product of that second diagonal. Now, this is just a 2x2 matrix, and we can apply this same process to any 2x2 matrix. But there's also a variation of this that works for 3x3 and 4x4 and so on. And so let's take this one step further to define this for a 3x3 matrix, so one with 3 rows and 3 columns. We can say that the determinant of the matrix, and here we'll just label with 3 rows and 3 columns, so we'll call A1, B1, and C1, as well as A2, B2, and C2, and A3, B3, and C3. The determinant of this matrix, again to be denoted with the vertical bars, is defined by, here we have our vertical bars, the determinant of A1, B1, C1, A2, B2, and C2, A3, B3, and C3. And this is where it gets a little bit interesting because there's not an easy way to like multiply through diagonals in the way that we did last time and still include all of the values. And so what we're actually going to do here is start with the first value, A1. And then from there, we're going to eliminate everything in the same row and everything in the same column. And what that leaves us with is a 2x2 grid, right? A matrix that looks fairly similar to what we just worked with. And we'll take that matrix and find the determinant of that. And so we'll take the matrix B2, C2, and B3, C3, and find the determinant of that. And we'll take the product of these. And that's our first step. Next, similarly, we'll move on over to the second value in our first column, the second value in our first row, B1, and we will multiply negative B1. And this is just a specific weird case where we're always going to subtract that second term. But in this case, we'll subtract B1 times the determinant of the matrix that's formed in a similar way, right? If we start here with B1 and eliminate everything in the row and column, then that's going to leave 4 values here that we'll use to form their own matrix. So A2, C2, and A3, C3. And we'll take the product of B1 with the determinant of that matrix. And then finally, we'll look at our third term in that first row, C1, and add C1 times, once again, if we look at C1 and eliminate everything in its row and column, that leaves us with a 2x2 matrix, which would be A2, B2, A3, B3. And so when we take the determinant of that and multiply it by the product C1, add it to our previous two terms, that's what we'll need to do to compute the determinant of a 3x3 matrix. And so we can simplify this out further because we know how to take the determinant of each of these. And so we can call this A1 times B2 times C3, right? The product of this diagonal minus the product of this diagonal, C2 times B3. And then minus B1 times the product of our first diagonal, A2, C3, minus the product of our second diagonal, C2, A3. And then finally adding C1 times the determinant of our last matrix, which would be the product of A2 and B3, A2 and B3, minus the product of B2 and A3, B2 and A3. And so that entire expression would represent the determinant of a 3x3 matrix. Now again, all of that might still feel very abstract. After all, we're still just using A1 and A2 and B2 and C3 and all of these variables to fill in for some arbitrary number. So let's see if we can actually look at a real example and compute it from there, and hopefully that will make it a little bit more tangible. So let's say we had the matrix 2, 1, 7, negative 5, 6, 0, and negative 4, 3, 1, and we wanted to compute its determinant. The first thing that we're going to want to do here is look at that first value of 2. Right? We know that this is going to equal to 2 times the determinant of the matrix that we form if we eliminate everything in the same row and same column as 2. So that leaves us with 6, 0, 3, 1. Right? These 4 values here. This, of course, now that we know how to evaluate 2x2 matrices, is something that we can compute more directly. We can say this is 2 times the product of this diagonal, so 6 times 1, minus the product of this diagonal, or 0 times 3. Simplifying this a little bit further gives us 2 times 6 minus 0, or 2 times 6. Next, we'll want to move to our second point here, 1. And again, we can say minus in this case, since it's the middle term and we're going to subtract the middle term, but minus 1 times the determinant formed when we cancel out everything in the same column and everything in the same row as 1, leaving us with the matrix -5, 0, -4, and 1. If we take the determinant of this, we'll have -1 times the product of the first diagonal, so -5 times 1, minus the product of the second diagonal, 0 times -4. Simplifying this further is going to give us -1 times -5 times 1, or -5, minus 0 times -4, or 0. In other words, -1 times -5, or simply +5. And then lastly, we'll look at our third term here, the 7. And so we'll take +7 times the determinant of the matrix formed if we cancel out everything in the same row and same column as 7. So that leaves us with -5, 6, -4, 3. Computing this determinant is going to give us +7 times the product of this diagonal, so -5 times 3, minus the product of this diagonal, so -4 times 6. And simplifying this, we'll have 7 times -5 times 3, which is -15, minus -4 times 6, or 2 negatives make a positive, so +4 times 6, giving us +24. Then adding these together, -15 plus 24 is going to give us +9, and so we'll have +7 times 9. And finally, doing the last bit of arithmetic here, we've got 2 times 6, which gives us 12, -1 times -5, those two negatives make a positive, so we have +5, and then +7 times 9 would be +63. And so if we add all these together, 12 plus 5 gives us 17 plus 63, and 17 plus 63 is equal to 80. And so 80 would be the value that is the determinant of this big matrix here, and would represent our final answer. So hopefully this is helpful so far. This can feel like a lot of computation at first, but ultimately it is just an algorithm. And once you can get the hang of that algorithm, as long as you're careful with the small details of the steps along the way, right, doing the multiplication, the addition, keeping track of the negative signs, etc., with a little bit of practice, this can quickly become an operation that you're really familiar with and can feel really confident in. We'll pause here for now on this video, but in the next video, we'll take a look at how we can utilize determinants to actually get to a solution of a system of equations. In the meantime, I hope you enjoyed this one. Thanks for watching, and I hope you have a great rest of your day.